Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Abdullah Al Hamid. Today we are presenting our LVAD's new designing. But first we need to know what is LVAD and why do we need to change it. So LVD, it's a left ventricular assistant device. It's suitable for patients that are waiting for a heart transplant, or it can act as a long-term when transplantation is not possible. Although LVAD are very important life-supporting device, they still have several major limitations. One major issue is thrombosis, where blood clots can form inside the pump due to the stagnant flow reasons. Another issue is hemolysis, where red blood cells are damaged because of a high shear stress inside the pump. Mechanical parts can also experience wear, especially when friction occurs between moving components. In addition, any failure in the pump system can create serious risk to the patient. The AeroHeart concept, what we are planning to do in this project, aims to solve these problems by using a next generation design based on magnetic levitation. By reducing physical contact inside the pump, the design can reduce friction, improve blood compatibility, and make the device safer and more suitable for specific patients, especially pediatric patients.
Now I'll be talking about the design, architecture, and trades-off. After re-evaluating the use of centrifugal pump, we decided to use axial pump for pediatric patients. This is because the design of centrifugal pump is wide and flat, because it relies on radial acceleration, where the blood flows from the center of the impeller to the outer volume. Thus, it requires a bulky outer casing, which is known as the volute, where the device will become too large to fit within a small child's chest cavity. In contrast, axial pump utilizes a slender, cylindrical geometry where the blood flows in straight line parallel to the spinning shaft. This streamlined shape allows for a significantly smaller radial footprint, making it much easier to implant in pediatric without compromising the surrounding organs. The axial pump is chosen for ultra-miniature design because of the trade-off between pressure and blood safety. Designing for ultra-miniature scale requires balancing between pressure and blood safety. So as for size versus speed, because of axial pumps are smaller, therefore they need to spin at higher velocities in order to generate the necessary pressure. Next, it is safety priority. In order to prevent hemolysis, which is the rupturing of red blood cells, the impeller design is meticulously optimized to maintain high flow rates without excessive rotational heat or friction. Lastly, is the levitational strategy also need to be reconsidered in order to fit this smaller scale. Therefore, we use hybrid approach. For hybrid approach, there are two parts, which are the permanent magnet and electromagnetic actuator. As for the permanent magnet, the job is to keep the impeller center side to side. The benefit of this permanent magnet is that they do not need any wires or batteries. Next is the electromagnetic actuator. A small electromagnet acts like a smart pilot, and the benefit of this is it only uses energy when it needs to move the impeller, keeping the device small and cool. So now we will talk about the risk analysis. So the first problem is the sudden power loss. Magnetic levitation requires a continuous electricity in order to keep the impeller floating. If the external power accidentally disconnected or the batteries fails, the magnetic field will collapse immediately. The spinning impeller will lose its position and crash into the internal walls of the pump, causing a seizure and potentially damaging the blood through extreme friction. Therefore, we need an emergency capacitor or a secondary battery. This acts like a mini power reservoir that provides enough energy to keep the impeller levitated for a few minutes, which is long enough for the patient to swap batteries or plug into a wall outlet. Next is sensor interference or failure. The system uses Hall effect sensors to monitor exactly where the impeller is 10,000 every second. If these sensors are damaged or confused by a strong magnet like MRI machine or a security scanner, the pump may lose track of the impeller's position. This controller might send the wrong signals to the manex, causing the impeller to wobble violently or hit the housing. Therefore, we need a sensorless control logic. Program a sensorless backup mode into the software. This allows the computer to guess where the impeller's position by looking at the electrical echoes coming from the motor coils. If the primary sensor fails, the pump automatically switches to this backup software logic to keep the propeller centered. The last risk is the controller software crash. The maglev system is controlled by a high-speed microprocessor. Like any computer, the software may crash. If the software stops calculating the magnetic adjustment, the impeller will immediately fall out of its floating position. Therefore, we need a mechanical touchdown bearings as our solution. As a physical safety net, the pump housing should be lined with mechanical touchdown bearings made of super smooth, biocompatible materials like ceramic or diamond-like carbon. If the electronic fails completely, the impeller will only fall on these smooth surfaces and continue to spin safely for a short time, preventing the device from locking up entirely.
Next, we move into the physiological limitation of fixed-speed LVAD system. The current AeroHeart Alpha prototype operates at a constant rotational speed. However, the human heart does not function at a fixed output. In a healthy cardiovascular system, the cardiac output continuously changes depending on the body's metabolic demand. For example, during resting condition, the heart typically pumps around 5 liters of blood per minute. However, during exercise or physical activity, the cardiac output can increase significantly from 15 to 20 liters per minute. A fixed speed LVAD cannot naturally respond to these physiological changes. As a result, there are several complications may occur. First, during exercise, the pump may fail to provide sufficient blood flow, leading to the inadequate systemic perfusion and reduced exercise tolerance. Second, during low demand conditions such as resting, the pump may over unload the ventricle. This will cause ventricular suction event, where the ventricular wall collapse inward due to the excessive negative pressure. In addition, a fixed speed operation may contribute to pulmonary congestion and unstable hemodynamic because the pump cannot dynamically adapt to changes in preload and afterload. Therefore, for the modern LVAD system, it requires adaptive physiological control mechanism that can continuously regulate the pump performance according to the patient's real-time condition. So this create the need for an intelligent closed-loop control system. Now, we're going to the adaptive control architecture for AeroHeart maglev LVAD. The main objective of the system is to automatically adjust pump speed based on the patient physiological demand, allowing the LVAD to behave more like a natural heart. The adaptive system operates using a closed-loop control mechanism. So, there are several physiological sensors that are integrated into the LVAD system, including the accelerometer, pressure sensor, flow sensor, heart rate monitoring, and Hall effect sensor for rotor position monitoring. In addition, the system can also implement sensorless estimation method using motor current and pump flow signal to estimate the preload condition without requiring invasive pressure sensor. So, when the patient transition from resting to exercising, body movement, venous return, and heart rate increase. These physiological changes are detected by the sensor and sent to the controller. The controller then processes the incoming data using either PID controller or an AI-based adaptive algorithm. Based on the physiological demand, the controller gradually increases the pump rotational speed to provide the greater blood flow and maintain the adequate systemic circulation. During resting condition, the controller reduces pump speed to prevent excessive ventricular unloading and minimize the power consumption. There are several research studies support this adaptive control approach. The first study shows that develop a sensorless adaptive controller using deep convolutional neural network CNN to estimate the preload condition and automatically regulate the pump speed during exercise. The second study proposed a multi-objective physiological controller capable of responding dynamically to preload and afterload changes. The third study shows demonstrated that additive speed flow control using Hall sensor feedback could maintain the stable maglev operation while increasing the cardiac output during exercise. So, because the AeroHeart system relies heavily on the magnetic levitation and real-time sensor feedback, several safety mechanisms are also necessary. These are include redundant Hall sensor, backup sensorless control mode, emergency low speed operation, watchdog software monitoring, and backup battery or capacitor system. Overall, the additive control system improves the physiological responsiveness, enhances the exercise tolerance, reduces suction risk, and increases the long-term patient safety and quality of life.
I will explain the regulatory pathway for the AeroHeart LVAD, specifically the difference between verification and validation, improving the safety and efficacy of the device. So verification focuses on engineering specification, which in simple terms, it answers the question, did we build the device right? So we have 5 points, which is first the flow target. The AeroHeart LVAD successfully achieved a blood flow rate of 6 liters per minute, which matches the normal cardiac output required for adult circulation. Secondly is the pressure head, where we are able to maintain 100 millimeter mercury, showing that it can generate sufficient pressure to support systemic blood circulation. The device operated below 5 watts, indicating good energy efficiency and reduced heat generation. As for the computational fluid dynamics or CFD testing was used to optimize the fluid flow inside the pump and minimize turbulence or stagnation zones. And for the last part is hemocompatibility. In vitro bovine blood testing showed low hemolysis levels, meaning the pump causes minimal damage to red blood cells. Overall, these tests verify that the LVAD meets its intended engineering and performance specification. Next is validation. Validation focuses on clinical needs and answers the question, did we build the right device? So the first is the preclinical trials, where large animal studies using sheep or calves are required to evaluate long-term safety, thrombosis risk, and infection risk, and pump durability inside a living body. The other one is ISO 10993, where the standard evaluates the biocompatibility of the materials to ensure the device is safe for implantation and blood contact. The other one is ISO 14971, which is comprehensive risk management by identifying possible hazards and implementing mitigation strategies. Human factors are also one of the point in validation, where usability testing ensures that patients, caregiver, and clinicians can safely operate the controller, alarms, and battery system. Last but not least, finally, all safety data and preclinical results are submitted to the FDA before approval for first-in-human clinical trials can be granted. In conclusion, verification confirms that the device meets engineering requirements, while validation confirms that the device safely fulfills clinical needs before human implantation.
Okay, my name is Muhammad Najmi Bezanuddin, and I will explain about the engineering, the future of the left ventricle assist device. So first of all is the compact pediatric architecture, which is we want to transitioning to a slender axial flow design to safely fit the restricted chest cavities, which is we want to make it a little bit smaller so that it can be fit on the child size. No matter how the size is big or small, actually, as long as the functioning as same and can be still work like usual for another 20 years. So this device can be considered as good because we can implant it just on the child, so it can be used until it's reached or like 20 or 15 years later. Okay. How is we want to do to make the size a little bit smaller is the next second is the we use the hybrid magnetic levitation innovation, which is we combining the permanent magnet and the actuator for the frictionless. By use this we can have a little bit friction may occur on the device when they use uh, inside this body. And then we also make its power efficient levitation. So that is how we want to make this happen in the future. Then next is multi-layer safety system. This which is the we use integrated capacitor is for the backup if the motor suddenly shut down. So this is how we want to do so that the device still can occur, still can work like usual. We'll also use sensorless logic so that if there anything happen, so the sensor can detect it's what part is broken and so on. Then we also make the other part to back up that part. Then and the last is the touchdown bearing for the fast fail safe mechanical reliability. So we use the bearing as the mechanical backup if anything happen. Net is last we can use in the future. I no The idea for the future is the adaptive physiological control, which is we can say it as AI to or any programming so that the device can adapted to the real life we can say as real life monitoring. So if the body, for example, if the body want to run and then he start to running a little bit and until he run like usual, so the device can detect it and increase uh, the the VAD VAD function. So VAD will be more faster pumping the blood. And if they want to resting or relax, so the VAD will slowly lower the pumping of the blood. And then this cause a result of a resilient miniaturized device that can mimic a natural cardiac response and also prioritize both technical excellence and long-term patient quality of life. Okay, that's all for my part in this future of the VAD.